Ladies and gentlemen, so today and tomorrow we're going to finish discussions about the last thing in bonding, and that is molecular geometry, which is why I have all the crazy balloons up here. Molecular geometry is how molecules would look in real space if we could zoom in at the molecular level and actually see them. We've been doing Lewis structures that are a two-dimensional representation of something that exists in 3 dimensions. Now we're going to take those Lewis structures and expand them back out into 3 dimensions and talk about their geometry. Now, when I talk about geometry, what do you usually, when I say the word geometry, what do you usually mean? What do you usually think? Okay, shapes, right. Math, but shapes. So when you think about geometry, you think about shapes, and that's what molecular geometry is. It's the shapes the molecules actually take. Now, the basis of molecular geometry is the idea that unshared pairs, this represented by blue, and bonding pairs, not seen, are they exert repulsion. Electrons are negatively charged, so they repel other electrons. So whether you have an unshared pair or a bonding pair of electrons, those pairs form a domain, and each domain repels other domains, just like balloons repel other balloons, because they're big and tend to be statically charged, like electrons. Okay. VSEPR, or sometimes just called VSEPR, is the idea that bonds are domains, those unshared pairs are also domains, electrons repel, those domains repel each other, and unshared pairs repel more than others. It's called valence shell electron repulsion theory, VSEPR. Valence shell electron repulsion theory. In other words, valence shells form electron pairs, and when they bond, and those electron pairs repel each other. VSEPR. Now, if you had 2 domains that wanted to repel each other as much as possible, what shape would they form? Okay, let me actually use another word. If you and your boyfriend had a fight, and you wanted to get as far away from each other as possible, where would you go?
Miami.
One would go to Miami, and the other one would go to
Orlando. They have to be in Florida.
California. Okay, one would go east, and one would go west. So if you have 2 domains that repel each other, they make this shape. They would get as far away from each other. What would you call this shape? A dumbbell? That's a good guess, or good conclusion. What else? How are they arranged? Or vertically, but they're arranged in a, they're in a line. So the geometry that is formed when you have 2 domains is called linear. It's just a line. It's linear. So if you have 2 domains, they orientate themselves as far away as possible. They make a linear geometry. If you have 3 domains that orientate themselves as far away as possible, what shape do they make? Yeah, they make a triangle. They make a Mercedes symbol. Okay? So this is Mercedes planar. I mean, triangle planar. So if you have 3 domains that orientate themselves as far away as possible, they make a triangle in a plane, or trigonal planar. Now, understand, the actual domains you're going to hear about from me, from the internet, is going to be the adjective, the fancy sciencey term. If you call it triangle plane, because it's a triangle in a plane, I'm going to call that okay. But realize on test questions and in multiple choice examples, it's going to be trigonal planar. Because it's a triangle plane. It makes a plane in a triangle. or make a triangle in a plane, trigonal planar. Okay. So far, so good? I'm going to bring up a graphic in a second. But this one's kind of cool. This is my favorite. How many domains exist here? 4. Anyone ever played that crazy block dropping game where it goes dun 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 dun, and you drop a block and here's the lines? What's that called? Dun, 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 dun. You get the long block and they and you drop it and you drop it. Tetris. Yeah. Anyone ever played Tetris before?
Talking about the
Atari,
Atari.
Nintendo,
Well, I don't
Game
remember
Boy.
the old one.
Because you weren't born then.
Yeah, exactly.
I was born. When I was your age, we were playing Tetris on our Game Boys and changing out batteries every 2 hours.
I only know it. I saw a video on the guy beating.
Yeah, Tetris is pretty cool. Anyway, tetra means 4. This forms a tetrahedron. When you have 4 domains that orientate themselves as far away as possible, it makes a tetrahedron. And we call it tetrahedral geometry. Tetrahedral. Tetra means 4. We have an advantage because my generation played Tetris. You can play Tetris. You just get on your phone and type in Tetris, and there's lots of things you can play in Tetris. So tetrahedron, 4. Woo, flying tetrahedron, flying tetrahedral geometry. Now, there's 5 or 6. They have other special geometries, but we're going to learn about those later. Now, these geometries are called the fundamental geometries or the electronic geometries. When all you have are domains, and we don't care about what type of domains they are, we have a fundamental geometry, sometimes called an electronic geometry. Now, to find the geometry of a molecule, you start with the Lewis structure. You draw the Lewis structure, and then you count the number of domains around a central atom. If there are 2 domains, it is linear. If there are 3 domains, it's trigonal planar. If there are 4 domains, it's tetrahedral. If there are 5 domains, then you get a triangle pyramid on top of a triangle pyramid. This is called trigonal bipyramidal. Trigonal bipyramidal. And if you have 6 domains, then you have a square pyramid on top of a square pyramid. It makes an 8-sided shape, and we call that octahedral. It makes an octahedron. So much writing.
I have a question.
Yes.
Okay, so how do you tell again, like, what are the domains? Like,
Domains are the dots or the sticks. So if you were to draw water, we remember that water looks like this. Oxygen having 2 unshared pairs, unshared pair, unshared pair. Hydrogen on the other side. So that's water. Fix that up a little bit. Okay. So how many domains do we see with water?
4?
4. The unshared pairs are a domain. And then the bonding pairs are a domain. Okay. So water has 4 domains. Water's fundamental geometry is tetrahedral because it has 4 domains. 2 bonding with the hydrogen and 2 unshared with the unshared pairs.
So,
Sounds like you have a question. Yes.
I think so. If you have like, so if you just had oxygen, wouldn't you have 3 tetrahedrons, or not trigon, whatever it's called? I forgot it.
If we got room
So if it
on
was
the
just
hydrogen,
oxygen, how many would it have?
it wouldn't have a geometry because it would just be
It would just
molecule.
be itself.
Yeah.
Okay, it's only.
We only look at things versus other things.
Okay.
Okay. Does that idea make sense? There are 4 geometries. So within the fundamental geometries, or the electronic geometries, there are molecular geometries. And that's what we really care about. Just like we have bond dipoles, but we care about the molecular dipole, we have electronic geometries, or fundamental geometries, but we care about the molecular geometries. And all of the geometries from trigonal planar on can be broken down further into molecular geometries. We care about, in this class, trigonoplanar and tetrahedral geometries. So we're going to break down trigonoplanar and tetrahedral. Trigonal bipyramidal and octahedral have a whole bunch. We don't care about those. You might care about them if you take chemistry AP. I don't care about them in this class. Yeah.
So N2 is a trigonoplanar.
Nope. N2 is linear because it's just two things.
N2 is the triple bond in the middle and then two unshared pairs on each side, but it's not a domain for each unshared pair.
Yes. So it's one on this side, one on this side. Oh, and the double and triple bonds count as one domain. So it's domain, atom, atom, domain, domain. So it'd just be linear. Other questions?
Can you expand on that?
Yes. To draw it out, well, you asked it about N2. N2 is, hey, look, it's like your test. N2 is that. So that's a domain, and that's a domain. So it's basically linear here and linear here. So it's linear and linear.
But the three domains look kind of, it's still linear.
Because we look at the domains around a central point or a central atom. Okay, this is water. Hi, water. Can you see how the blue represents the unshared pairs and the yellow represents hydrogen? And what you can't see in the middle is the oxygen. Okay. Oxygen's in the middle, hydrogen domain, unshared pair domain, unshared pair domain. This is water. How many domains does water have? 4. But of those 4, 2 of them are unshared. Unshared, unshared. And 2 of them are bonding. Bonding, bonding. So we have to have a name for what this is. What kind of molecular geometry do you think you would see if you had a name for it? Ignoring the unshared pairs, how does water look? 2 thingies. How does the water look? Ignoring the unshared pairs. Say again?
Linear.
Linear? Is it linear?
Wow. If you not to, then you get it.
I see what you're saying. Okay, don't ignore them. Realize they're there, but don't include them in the shape. Look like a triangle, right? Well, it has a special name. It's called bent. If you have a trigonal fundamental, or sorry, you have a tetrahedral fundamental geometry, but 2 of them are unshared, then we call it bent. Water is bent. And the reason we call it bent is the unshared pairs are basically invisible. Yeah.
When you get a triangle, there's only. But you said those 2 don't have.
Yeah, pretend the oxygen is there.
Then you got 2 balls.
Hydrogen, oxygen, hydrogen. Hydrogen, oxygen, hydrogen. Bent. Okay. So if you have a tetrahedral fundamental geometry, but 2 of them are unshared, we call it bent, as in water. If you have a tetrahedral fundamental geometry and 1 of them is unshared, as in ammonia, NH3, can you see the N in the middle right there? In your mind's eye, you can see the N, the nitrogen. NH3, then you have the geometry that is called trigonal pyramidal, triangle pyramid. Trigonal pyramidal. Woo, trigonal pyramidal. We can throw a trigonal pyramidal molecule around. Again, fundamental geometry is tetrahedral, but because 1 of those geometries is unshared, the overall molecular geometry is trigonal pyramidal, triangle pyramid. Oh no. It appears we have a leaky molecule. Okay, does that make sense? Now, going back to 3 domains, I skipped over 3 for a reason. Going back to 3 domains, are we good to go back? We only have a few minutes left in class, so I just want to make sure we're good. Okay, going back to 3 domains, if all of those domains are bonding, then you just have your triangle plane, your trigonal planar again. So if they're all bonding, then the fundamental geometry is the same as the molecular geometry, triangle planar, trigonal planar. But if one of those domains, we have a leaky domain right here. If one of those domains, imagine it's bigger. If one of those domains is unshared, and we only have two bonding, what do you think we call it again?
Bent.
It's bent again. Yeah, it's making that V shape. It's bent again. So if you have a trigonal planar fundamental geometry, but one of those domains is unshared, then you get a bent molecular geometry. Is this idea kind of making sense, starting to make sense? It's what they really look like in real life. I don't know how long these balloons are going to last, but here they are for now. They probably won't make it until Friday for their unit test.
This is going to be on test on Friday, right?
That's the plan, unless you'd rather have it on Thursday. There's a lab on Thursday, and it's pretty fun, but I'm not sure you're going to learn any more that you already haven't learned. So that's the plan. Test on Friday, unless you'd rather have it on Thursday. Okay, next. 5 domains is Trigonal Bipyramidal. It has a bunch of subdomains, or sorry, 5 domains is Trigonal Bipyramidal. It has a bunch of subgeometries. I don't care about those in this class. Okay. Yeah. So, in case you're wondering, they're called seesaw, T-shape, and linear. And then the 6th domain is octahedral. Octahedral has a whole bunch of others: square pyramidal, square planar, linear, a whole bunch of the square pyramid. Anyway, we don't care about those. What we do care about is the fundamental geometry. When you have 6 domains, 1, 2, 3, 4, 5, 6, they form an 8-sided shape called octahedral. And I'm sorry, I could not build it for you. I'm just not that good. You have to use your imagination. Octahedral?
Well, it's 6. What are these 6? Is there
4 making a box, 1 on top, 1 down below. So, an octahedral geometry is basically, imagine you have 4 making a box, 1 domain there, 1 here, and then 1 going up, and 1 going down.
Yeah, okay.
Oh.
I was thinking of like.
So it's
1
like
and
a,
6 there.
it's like a rhombus.
Like a rhombus, yeah. Exactly. Okay, questions? Yes.
So, are the atoms from like Jimmy Neutron wrong? Or like everything we know is wrong?